Welcome, data enthusiasts, to another exciting journey in our machine learning series. I'm thrilled to be back with you, and today we're diving into a regression task using a powerful tool from the Interpret library. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along effortlessly. Let's get started by setting up our environment and loading our tools to explore a fascinating dataset about diamonds. I begin by installing the Interpret library in Colab with pip3 install interpret. This is our gateway to explainable AI, and it's going to add some serious clarity to our model. Next, I import the essentials: NumPy for numerical operations, pandas for data manipulation, and Seaborn to load our dataset. From sklearn, I bring in train test split to split our data, and mean squared error and our toScore to evaluate our model's performance. Then, from Interpret's Glassbox module, I import regression tree, our star model for today, and the show function to display our explanations. With our toolkit ready, I'm set to load the data and start exploring. Now, let's load the dataset. I use Seaborn's load dataset function to grab the diamonds dataset, and I call dropna to remove any missing values. Though this dataset is clean, so we keep all 53,940 rows. A quick df.head gives us a glimpse of the data. Carat 0.23, cut ideal, color E, clarity SI2, depth 61.5, table 55, price 326, X 3.95, Y 3.98, Z 2.43. The next row shows carat 0.21, price 326, small diamonds, small prices. This dataset is a treasure chest of diamond attributes: carat for weight, depth and table for proportions, X, Y, Z for dimensions in millimeters, and price in dollars as our target. It also has categorical features like cut, color, and clarity, but we'll focus on the numeric ones for our regression task. With the data loaded, I need to prepare it for modeling. I define X as the numeric features we'll use: carat, depth, table, X, Y, and Z. These capture the physical aspects of the diamonds that likely influence price. For Y, I set the target variable as price, the dollar value we're predicting. Next, I split the data using train test split, allocating 20% for testing and 80% for training, with random state 42 to ensure reproducibility. This gives us X-train, X-test, Y-train, and Y-test ready to feed into our model. The stage is set. Let's build our regression tree. Here's where the magic happens. I initialize the regression tree from Interpret's Glassbox module. This isn't your standard sklearn decision tree. It's designed for interpretability, making it perfect for our XAI flavor. I call fit on X-train and Y-train to train the model, letting it learn how features like carat and depth predict diamond prices. Once trained, I make predictions on X-test with the predict method, storing them in YPred. To evaluate performance, I calculate the mean squared error and R-squared score. The results? Mean squared error is 2,035,775.8958. Root that, about $1,426 off per prediction. R-squared score is 0.8719, meaning 87.19% of the price variance is explained. For diamond prices ranging from $326 to over $18,000, that's a solid start, but there's room to improve. Let's dig deeper into why these predictions are happening. Now, let's explore the global explanation to understand what drives our model's decisions across the entire dataset. I call dt_regressor.explainGlobal and display it with show. On screen, you're seeing the global explanation plot, a piecewise linear representation of how features impact price. The root node splits on carat less than or equal to 1.00, with an expected value of 3,939, right in the middle of our price range. If carat is less than 1.00, it branches left to Y less than or equal to 5.54, expected value 1635, smaller diamonds, lower prices. Further down, carat less than or equal to 0.47 gives an expected value of 1,060, tiny stones. On the right, carat greater than 1.00, leads to y less than or equal to 8.19. Expected value 8,159. Bigger diamonds, bigger bucks. Further splits like y less than or equal to 6.79. Expected value 6169, and y less than or equal to 7.82. Expected value 12,316 show how dimensions amplify price. Impurities, like 566,830.87 at y less than or equal to 6.79, tell us where the tree reduces variance most. Carat and y dominate. Size is everything in diamond pricing. Let's zoom in on a single prediction with a local explanation. I call dtregressor.explainLocal on the first test sample. X test slice 0 to 1 and Y test slice 0 to 1, and display it would show. The output isn't printed, but the visualization would show the feature contributions for this diamond's predicted price. Based on the global tree, if this diamond's carat is, say, 0.23, like our head's first row, it'd follow the left path. Carat less than or equal to 1.00, then y less than or equal to 5.54, y is 3.98, so yes, down a carat less than or equal to 0.47. Yep, 0.23 fits, landing an expected value around 1060. The true price is 326, so our model overestimates, but the path shows carat and y as key drivers. This local view highlights how the tree navigates for one diamond. Small carat, small y, low price. Let's reflect on these results in detail. The mean squared error of 2,035,775.8958 translates to an average error of about $1,426 per prediction. Not bad for prices spanning 326 to 18,823, but it suggests some diamonds are tricky to predict, maybe due to unmodeled factors like clarity or color. The R-squared score of 0.8719 tells us the model captures 87.19% of the price variance. Strong, but that remaining 12.81% hints at room for improvement, perhaps by including categorical features or tweaking the tree's depth. The global explanation plot you're seeing shows carat as the root split at 1.00. Expected value 3,939, splitting small from large diamonds. The left path to y less than or equal to 5.54. Expected value 1635, and carat less than or equal to 0.47. Expected value 1060. Nails small diamonds like our head's 0.23 carat. Price 326. The right path to y less than or equal to 8.19. Expected value 8159, and y less than or equal to 7.82. Expected value 12,316 captures pricier stones. Size drives value, and the tree knows it. Looking at the global plot again, the impurities are telling. 566,830.87 at y less than or equal to 6.79 means that split slashed a ton of variance, pinpointing where dimensions like y, width, refine price predictions. The expected values climb as we move right. 1060 to 12,316, mirroring how carat and y scale prices up. The local explanation for our first test diamond would echo this. Carat 0.23 and y 3.98 follow the low price path, but the model's $1,060-ish prediction versus the true $326 shows it's overestimating for small stones. This interpretability is the XAI flavor. Regression tree structure lets us trace every decision, from root to leaf, understanding why a diamond's price lands where it does. To wrap this up, we've taken the diamonds dataset, a glittering collection of 53,940 gems, and trained a regression tree model to predict prices, achieving an R-squared of 0.8719 and a mean squared error of 2,035,775.8958. The global explanation revealed carat and y as the heavy hitters, splitting small diamonds at $1,060 and big ones at $12,316, while the local view showed how one diamond's price prediction followed that path. This model's interpretability, those clear splits and expected values, gives us a taste of XAI, letting us see the why behind the what. Grab this code, play with the features, maybe add clarity or cut to boost that R-squared. I'm thrilled with this diamond dive. Hope it's got you shining with ideas. See you next time for more data adventures.